Welcome to lecture number 11 for module 2. In lecture number 10 we saw that PSS, that is very useful for the improving the dynamic stability of the system, can be used to improve the dynamic stability. As we know, the dynamic stability is a, or you can say, small disturbance stability. When there is a sudden but small disturbance takes place, that is basically known as the small signal stability. In last we saw this block diagram of this is known as the power system stabilizers. They are used to stabilize the generators or stabilize the system with the help of giving an input signal here to your exciter that is going to your machine. So this is the terminal voltage transducer I explained on the last turn. Here we are measuring the terminal voltage V1, and then here is the blocks, means it is a gain of a power system stabilizer, and the input to the power system stabilizer is the change in the rotor speed, that is a speed deviation here. This is given to the gain, that is a K here stabilizer gain, and this gain is, after that it is going to wash out filter, where we filter out some of the unwanted harmonics, and then it is passing through the lead compensators. Because here whole circuitry we tried to put in the phase with the speed here, so that we can add in terms of here voltage. So this n here, the exponent it is written, in this case we have taken n is equal to 2, means there are the time constant T1, T2 and other time constant the T3 and T4s are taken, and this signal is coming to the here with the reference voltage here, the terminal voltage, and then we are giving another auxiliary signal to here, and then that is going to the exciter of the generator, and this finally EFD, which is generator, it is going to the generator terminal. So the tuning of the power system means we have to get the various parameters, we have to get the gain, that is very important. If your gain is not tuned properly, your system will be unstable. So the tuning of this gain is very important, and this gain depends upon the system operating condition. We know it very well that the system conditions keep on changing, means as you know the load is keep on changing, and that generator is following, means generation is also keep on changing. So your system in the terms of power is also changing. At the same time there will be some transmission line outages, means the network topology can also be changed. So the value of the gain choosing at any particular operating condition may not be suitable for other operating condition. So we should have a very gain suitable for the wide range of operating condition. So that's why we require the tuning of this power system stabilizer, so that it is very difficult to tune every moment. So we can go for the wide range of system operating condition. So we have to get the gain as well as the various time constants, those are required for proper use of this stabilizer. Basically that stabilizer are used to improve the small signal stability of the system. So the generators whose PSS has to be tuned, the inertia constant is made very high so as to disable its dynamics. So while going for the tuning, what we do, power system tuning, we make the machine inertia is very high so that its dynamics can be ignored, and only we can see the dynamics of the power system stabilizer, and then we can go for the tuning of power system stabilizers parameters. Rest of the system, because the generator will be connected to the system, and that rest of the system is taken as the infinite bus, along with of course some transmission line it is connected. With above assumptions, with these two assumptions, basically the transfer function for the voltage reference of exciter to be the electric torque input of the generator is found out just a GSYS, G system. The PSS lead lag time constants, as I said, T1, T2, T3, T4 are adjusted in such a way so that to compensate the lag in the transfer function of this, the total system transfer function. So we have to tune these parameters in such a way that we can have here compensate the lag which is available here in the G system, and then we can stabilize the system. After tuning, just we have to use those in complete system dynamics, and then we have to see the performance of the system. To go for the detailed model of the power generators, the Herfan Phillips model is very popularly used, and it is here just we have represented. You can see this is your Phillips Herford Phillips model of a generator. This model is suggesting the 9 states of this generator model completely. This generator here you can see H, if you remember we were using in the transient stability case as well. Here the Kd is the damping constant and this is the transfer function with respect to the change in the Tm minus Te, means here we can write the differential equation here change in omega r here, that will be equal to this multiplied by this, means you can see what we are getting here, it is Tm minus Te divided by here your means 2H S plus D. So this is nothing but your sink equation. Here this D, that is a Kd we have taken, that is a damping constant. So this again omega dot, that is a differentiation here, is basically not omega dot, it is omega, and then omega here if you are again integrating you will get the angle change in delta. So this is, you can say, state number 1, this is state number 2, here we have state number 3, we have another here 3 states, that is 4, 5 and 6, and here this is state number 7. So this total we have the 7 state. Here the exciter which is represented here directly, it is having itself the IEEE type 1 DC exciter, and that has the 3 states, and that we have represented in our formulation. I will see later that it is now for one machine. Here we are going to have the 7 states. So if your number of machines are Ng, then total number of state will be here multiplied by 7. So these will be the state of the total number of machines. Now in this case we have not considered the power system stabilizer. If you are going to use power system stabilizer, you have to use here one auxiliary system, and that is here VSS, that will be added here. So this again if you are going to include that, then again the states of your power system stabilizers are also going to be added, and the total number of this whole total state will be increased accordingly. So this is your exciter, just I have written the transfer function is Ex, is basically the transfer function of your exciter. This is your basically of the field circuit, because EFD is passing through this, we are getting the flux change in the your flux linkage FD, and multiplied by this we are getting, and this addition of this delta multiplied by K1 is giving you a change in your electrical output, and this electrical output is subtracted from the mechanical change in the magma. Here that you can see the change terms are written, means we have written here change in omega, change in delta, change in your Tm, change in T, because we have written this equation in the linearized form. So it is a linearized as per its operating point. So that's why it is everywhere you will find the differences that we are getting here, all that here the difference values, not the actual value, because if you go for this, you know these are the nonlinear equations, those are linearized one. So this is complete model of a generator including exciter, and this is nothing but your 7 state model. Now here the washout time constant can be value between this. Here in the power system stabilizers, if you will see here, just we have used here, this is a washout time constant Tw, and also we require the terminal voltage here, the Tr. So the time constant here can be taken as here already I have explaining here, the washout time constant can have a value between 2 to 10 seconds. For the local mode of oscillations, washout time constant is near about 1 to 2 seconds, and if inter area modes are also considered, then it will be range of 10 to 20 seconds, so it is a larger side. The PSS gain can be chosen by different methods like trial and error methods. As I said, the gains how you are going to choose, because the gain is very important for the performance of your stabilizer for which it is used. So if your gain is not proper, then your system, the power system stabilizer which is used to stabilize the system, may destabilize the system. So that is a, you can say, adverse impact. We don't want that. So the methods to choose the gain is, one is your trial and error method, root locus techniques. As you know the root locus, we can plot the roots and then we can see where this gain will be varied so that we can have the stable system. We can go for the linear control techniques. In this, it is a linear, like your linear quadratic regulator, and robust control are by optimization techniques. And then we can go for the genetic algorithm, particle swarm optimization, it is also called PSO technique, this is called your GA technique. Any non-conventional optimization techniques or conventional techniques that can be used, and then we can choose the suitable gain that can be for wide range of operating system. So if you are going to simulate your small signal stability in the large power system, or you can say multi-machine system where number of generators are more, then that can be analyzed to consider the dynamics of complete system. For small signal stability studies of a practical system, the detailed model of various components has to be written in state space form, and then linearized equations are derived. These components may include the various components, like we can include the speed governing system model, we can go for the turbine model, we can include the synchronous generator model, and that includes your excitation model, your excitation system model, your exciter model, and we can also include the power system stabilizer, then we have to model that one also. At the same time, we have to model the load, and if a load is having your dynamic load like induction motor load, that can be also modeled in terms of state space form. As we know, if you are going to model the machine in the simplest way, that is a two-order machine dynamics, then we have seen that it is nothing but you are writing here h upon pi. If you remember, here I wrote this differential upon dt square, this is d. Here it is we are getting the Tm minus T. This is your second order differential equation. So to represent this, we have to again go for the state space representation, means we have to write the two equations here. One we can go for this here in terms of omega, and other we can go for in the delta. So we can represent this equation into the two state space forms, and then we can use that. So this is your complete, I can say now we can write d omega t here, it is nothing but your this. So we can write this is equal to your Tm minus Te, here some constant k, this constant, and then we can write here d upon dt, it is nothing but your omega. So these two equations can be found from this double differentiation equations. So this is now state space form, and then we have to linearize, so that because here the terms are nonlinear in nature, t is a nonlinear function of sine delta, you know, is a p max sine delta. So we have to linearize so that we can have the linear, and then we can form our equation here x dot will be equal to your ax plus bu. So this is a state space representation of any system. Here this A is now is a constant matrix, and that is called state transition matrix, and this gives a lot of information, and based on this we can go for the eigenvalue analysis, and we can again go for the left and right eigenvectors, and then we can assess the performance of system based on the eigenvectors corresponding to the various eigenvalues. I will come to that point later. So the linearized model will provide the state matrix, as I said A, that is a state matrix. For building the state matrix, the following two approaches are normally followed. First one, the state matrix are built at a known operating point from finding the derivative of function with respect to state variables. Means we can find the matrix by the differentiating with respect to the state variable, and then we can get this state. Here after differentiation you have to find the coefficients at the operating point. Another is by using the perturbation approach around the operating point. Means your system is operating, now you can perturb by 1 to 5%, and then you can see the change in the variables, and then you can form the again state space state matrix. Eigenvalues of state matrix A provides the stability information of the system. as I said, if your eigenvalues, if any of the eigenvalues, the real part, if it is a positive, we can simply say our system is unstable. But if it is a negative real part, then it is said as a system is stable. The participation matrix, again I have defined this participation matrix in the previous lecture, can be formed corresponding to the critical eigenvalue after obtaining the right eigenvector and the left eigenvector matrices. Means we can calculate the REV and the LEV, that is a left eigenvector, and here it is your right eigenvector matrices corresponding to the critical eigenvalue. You know, if your system matrix is of several orders, so the eigenvalue will be according to that order. In the previous example, let's suppose we have the two machines, then it is 7 cross 2 will be the order of this your matrix. So we will have 14 eigenvalues, and we have to take the critical which is very close to your 0, that is your real and imaginary axis here. This, if it is very close to here, this is called the critical eigenvalue. In order to know whether the particular mode of oscillation is a tie-line mode or local mode, plot the speed eigenvectors of each generator corresponding to that mode. Corresponding to that mode, you have to plot the speed eigenvectors of each generators. If all the speed vectors in a control area are clustered together and are separated clearly from the cluster of vectors from other area generators, it is a case of tie-line mode. We will see the example of this tie-line mode. If these vectors are mixed up, if it is not able to, we cannot able to say about that, then it will be your local modes and local modes of stability problem. For building the state matrix in power system involving the differential and algebraic equations we are normally having, it is convenient to perform a small perturbation analysis to numerically evaluate the partial derivative. Means we can, as I said, there is two approaches. One, we can go for the linearizing at the operating point, and another that we can perturb from the operating point and then we can form the state matrix. So here we are just talking about the perturbing that to get this partial derivative. Starting from the initial condition, a small perturbation is applied to each state variable. The change in rates of change of all the state divided by magnitude of, here you can see this, magnitude of perturbation gives the column of state matrix corresponding to the disturbed state. So here the change in the rates of change of all the states divided by magnitude of perturbation gives the column. Here you know the column and another is row. So this is the column values you can get of this state matrix. The entries of state matrix are obtained by partial derivative, which are obtained by dividing the state derivative and the output variable increment by the perturbation. Here the entry of the state means row vector, we can get this. So a program structure you can see from this figure means you have to go for the first load flow because we require the initial operating condition. Then we have to again initialize the components of various states. For example, the delta, omega, all this we have to initialize. Then we have to list out the states, input and output variables, and then for each variable you have to perturb here. And then if you are perturbing the network solution, then you have to upturn, and after that you have to go for the dynamic commutation, then you can build your matrices, and this process is again repeated for all the variables, means that is state variables. To understand this how we are going for the multi-machine system, we will see the IEEE system, that is a two area system. Here this is a area 1, this is your area 2, where the two machines in this area, generator 1 and generator 2. In this area 2 we are having generator 3 and generator 4. So this is your nothing but area 2. Here I am calling this is area 1. So this is a 13 bus test system. You can see bus 1, 2, 3, 4, 5, 6, 7, 8, 9, here 10, 11, 13, 12 and 13. In this case, without PSS, what we did here, you can see this is the tie line, means these two areas are connected by a line here, double circuit line, that is 9 to 10 here, and you can see we are having the double circuit line, and this here third is a 13 bus line system. The system consists of 4 machines, as you see, the G1, G2, G3, G4, and it is having 13 buses. Generators 1 and 2 are in the area 1, generators 3 and 4 are in area 2. Generators G1, G2 and G4 produce 700 megawatt. However, your generator 3 is providing this 716 megawatt. Means here your this generator 3 is giving 716 and others are feeding the 700 megawatt, means here is a 700, this is your 700, this is also producing 700 megawatt. The power which is flowing here in this line from area 1 to area 2, it is nearly 423 megawatt, that is transmitted through the tie line, because the two areas are connected and the connection line is known as tie line. Each generator is equipped with the IEEE type 1 DC exciter, and the total load of the system here 2734 megawatt. Then what we did, we model the complete system with the 4 generators without PSS. So we are going to have our this 7 state for each generator, and then we are having this 4 generators. So we are going to have 28 states. You can see here these are the eigenvalues corresponding to the whole system. So you can see all the values negative, real part, you can say this is, this part here is a real part, this is your imaginary part, I with here I is attached with this, here it is your imaginary part, and this one is your real part. In this eigenvalues, you can see that the 2 eigenvalues are very close to 0. They are basically corresponds, they are representing the infinite system, because we are taking this generator connected with the infinite system. So that is a 0 or that is initial state, that is giving that one. Remaining are, you can see here your 28, you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26 and 2 states, because it is a relative one. So it is a 28 eigenvalues. Now you can see all the real part, as I said, for the stability criteria, we should have the negative real part here. So in this you can say all are negative, in this all are negative. In this real, you can see the 2 value vectors here, I can say 2 eigenvalues here is having here the positive, this real part, and as I said it is having the complex, so it will have the 2 eigenvalues, those are basically in the left hand plane. You can say if you are plotting here, this is your 0 axis, so this is your right hand side, this is your left hand side of this eigenvalue, this imaginary axis, this is your imaginary part, this is your real part. Now you can see the 2, these are plotted here and they are representing the unstable modes. So corresponding to this, our system is unstable. To see it, let us see here. This is here all these modes, because now we are going to have 28. You can see others are here 0 and they are very close to some of them. So here all are the stable modes of operation. Now we are just calculating the participation factor. Now we can see the participation factor. This is your corresponding to generator 1, this is corresponding to your generator 2, this is a corresponding to generator 3, this is a corresponding to generator 4. The first here value, the participation factor of unstable mode, means the participation factor of unstable mode which has the damping here and the frequency of this hertz. How? You can see, because this the value here we can calculate this from this value, you can see here we can calculate here this your lambda 1, it is nothing but your 0.0149 here minus 3.769, that is your imaginary, and again will be here you can say plus minus. So from here this is your nothing but alpha and this is your omega. So from here we can calculate the damping of the system, and it is calculated here, and we find that the damping here is negative here you can say, and due to this means your system will be unstable, and the frequency of oscillations that we can omega we can find out, and we will get this 0.4 Hertz oscillation. So you can see here that the two states, because one generator is having 7 state model. So here it is for up to generator 1, here for 14, generator 2, actually basically here 14 will be here, this is 15, this is your 21, and here it is up to 28. So this is basically corresponding to your state. You can see your the speed here, that is your the participation factor in magnitude, means the two states are participating, that is your change in your delta and change in here is the speed. So you can see this magnitude is participating much, and again then followed by third, then followed by fourth, and then it will be second. So they are basically, it is giving information who is participating how much in your unstable mode. To see this again, we can again as I said, based on your eigenvalue, critical modes, which is critical eigenvalues where unstable eigenvalues, then we again calculated this right eigenvector angles, and then we can find in this plane the angle of left eigenvalue eigenvectors angle. Here you can see for the generator 3 and generator 4 they are very close, means here G3 and G4 are closer together, and here G1 and G2 are closer together. It shows that the G1 and G3 they are oscillating with respect to G1 and G2, means there is a complete coherency, means here these generators are combined together, they are oscillating this group with this group. So it is nothing but your inter area modes of oscillation. It is a clearly we can say this is your tie line oscillation of the generators. If it is not possible to go for this, we cannot analyze, let us suppose the eigenvector angles are mixed up, then it will be your local, as I said in the beginning. Now we can also see the performance, that is the rotor angle oscillations for a 3-phase fault. We applied the 3-phase fault, you can see here, if you will see here, sorry. So this is you can say applied a 3-phase fault here, this is your 3-phase fault. Once we are applying, then the system performance, means how this machine dynamics, how this delta of this machine are changing along, again the delta as well as the speed we have plotted together, and we saw that as even though here in steady state the machine is unstable mode. So you can see here the delta here, this rotor angle, that is delta. Here you can starting they are very close, and then in the once time is passing here, it is you can say this is this gap is increasing, and then we can say our system is unstable. You can also system unstable. You can also derive a conclusion. You can see here this is generator 3 and generator 4, means these two are your generator 3 and generator 4, and here generator 1 and generator 2 they are almost coinciding each other. So the angle here you can see the generator 1 and generator 2 here. So you can again see here the clear separation of generator 1 and generator 2 with respect to generator 3 and 4. So they are just separating, and your system become unstable. Now you can see here the speed. Here just we have done the speed deviation. You can also here you can see the speed is keep on increasing, means the deviation of speed is keep on increasing here you can say constantly, and again you can see the generator, the speed of generator G3 and G4 here, G3 and G4. However, this is your speed of G1 and G4 and G2, means it is a coinciding together, and this is a separation, complete separation of these machines, the speed is increasing. This also shows that on the instability of your system followed by that fault. Now, for this system again, we want to put the power system stabilizers so that we can see how we can improve the stability of the system. The phase compensation provided by power system stabilizer lead lag block, that is the PSS of generator 2, just it is written here. So, the PSS, the phase value, it is here in the blue, and the ideal phase here is this. So, it is just, we are just comparing with the ideal, it is approximately it is following this. So, if frequency changes here, here phase is provided in this fashion. Now, the parameters here, the PSS parameters that has been used, and we are using the PSS at generator 3 and generator 4, because generator 1 and generator 2, they are very much close together, they are synchronizing at one bus. Here generator 3 and generator 4 are together. So, we have taken the washout filter time constant TW here 10 second, this is also 10 second. These are basically the time constant for the power system stabilizer. Once again I said here this was nothing but your 1 plus T1s over 1 plus T2s ke power n. Means here it is nothing but, if you are using second order, then it is 1 plus T3s divided by 1 plus T4s. So, this is your basically the lead lag phase of that, and where we require the T1, T2, T3, T4, those are the time constant. For this stabilizer we have used this time constant, and for this stabilizer we have used this. The gain we have used for both stabilizers are 300 each, and this is again based on the hit and trial method that we have obtained, although there are so many methods suggested for the gaining the proper gains of the power system stabilizer. Using this, here what we did, again we did for the same fault, and then we measure the rotor angle oscillation of power system stabilizer with the stabilizer here. Now, you can see the delta, now it is again in the narrow band, and then you can say the delta is here decreasing, and now it is going to be steady state. What that meant, if you are taking 1 as a reference, here all the 4 generators we are measuring. So, with respect to 1 here, any one you can take as a reference, then you will find that others are here, it is a constant. With reference to this, it is going to be 0. So, we saw here the rotor angle oscillation of all the machine with PSS, the power system stabilizer. Here you can see, if you are taking any one as a reference, then you are looking at that reference, you can see if this is your axis is this. So, angles here they are constant, and we can say our machine is stabilized, followed here the initially some disturbance. Similarly, we can see the speed also. You can say speed here is again suddenly changed, but later on here it is going to be here, that is a stabilized, and your change in the machine deviation is also constant, and almost it is going to be settled. So, your machine is settled. So, we can say now again here, this is your, with the help of power system stabilizer, we are getting the stabilized solution, and your system is stable with the help of the power system stabilizer. So, this is the beauty of power system stabilizer, but only the problem here, the power system stabilizer, if you are using the gains as well as the time constant must be tuned, means parameters of PSS must be obtained clearly for wide range of operating condition. That is why in our country we have generating stations, those are equipped with the power system stabilizer, but these units are isolated from the actual, because they are not tuned properly, and once they are putting this in the system, instead of stabilizing they are going to destabilize. So, the tuning is very important. So, the coordination of the power system stabilizer, this is again you can see the coordination of the various PSS in the system, means if a system is having, for this example we had the 4 generators. So, if suppose there are the 4 stabilizers, though they must be coordinated to each other, means once you are tuned for one system, you are tuned for another system, it may not be optimal solution, it may be having a different. So, the power system stabilizers in a system, if not properly coordinated, will result in the deterioration of the system damping. You can say the system performance or dynamic performance will be deteriorated, and system may not be stable in several cases. The parameters of all the power system stabilizer in a system must be found simultaneously using control techniques rather than designing separately. Many methods for the coordinations are available. in the literature like LMI techniques, robust control technique, linear quadratic regulator or linear quadratic Gaussian technique, etc. In the system there may be some facts controller, and they will also have some control for those devices like SBC, TCSC. These are the facts devices and they will be having the controller. If they are used for the damping, then they too must be coordinated with the power system stabilizer. Otherwise, what will happen, that may create another problem, and again whole system will be, instead of stabilizing, it will be the destabilizing. So we saw the importance of the power system stabilizer in this lecture, how they are very useful, and again how we can form the state transition matrix, and then we can go for the analysis for the small signal analysis of the system, including the various that is in multi-machine power system. So far we have seen the stability, that is angular stability. In that we saw the stability corresponding to the severe disturbance, that is your angle stability, that is known as a transient stability, and another we saw in angle stability, that is a small disturbance or a small signal stability. Now let us see the voltage stability. In the voltage stability, the mainly the concern, we are concerned about the maintaining the bus voltage. In those, that is your angle stability, as you saw, we were looking at the angle, or you can say the speed deviation of the machines. So it was known as the angle stability. Here we are concerned about the bus voltages of the system. Due to difficulty in the reactive power balance, means provision of the reactive power, this voltage stability comes into the picture. As per IEEE definition, and this IEEE form one dynamic performance subcommittee, and that working force given one IEEE document number this 19TH0358, that is a 2PWR 1990. In that, it is a title of that paper is a basically transaction paper, voltage stability of power systems, concept, analytical tools and the industrial experience. In that, they give the clear definitions for the voltage stability, voltage collapse and the voltage security. Voltage stability is the ability of a system to maintain voltage so that when load admittance will increase, both voltage and power are controllable. Voltage collapse, however, is the process by which instability leads to very low voltage profile in a significant part of the system, and that may lead to complete collapse or blackout of the system. However, the voltage security is the ability of a system not only to operate stably, means it is one step ahead, means your system may be stable, but some of the voltages at the buses will be violating. So it will be not the voltage security, means we have to operate stably. At the same time, the voltages at the various buses of the system must also be well within limit, that is your operating limits. So voltage security is the ability of a system not only to operate stably here, but also to remain stable as far as the maintenance of the system voltage is concerned, following any reasonable credible contingency or adverse system changes. Means whenever there is a credible contingency is going to come into the system, your system should be stable, as well as it must not to violate any of the constraints, that is we are talking here about the voltage constraints. As I said, in the operating constraints, it may be your line flow constraints, it may be your voltage constraints, it may be your transformer tapping constraint. So here in the voltage security aspect, we are only concerned about the voltages of the buses. However, the Segre, again he gave another definition for these three terms, that is a voltage stability, voltage instability and the voltage collapse. In the voltage stability, a power system at a given operating state, and subject to a given disturbance is voltage stable if voltage near the load approach post disturbance equilibrium value. Means if voltages near loads approach post disturbance equilibrium values, the disturbed state here is within the region of attraction of voltage post disturbance equilibrium. In the voltage, I will again come to the here the various terms, just we are using the region of attraction. looks something new term, will be again later on we will see. Equilibrium already I have explained this, what is the equilibrium. Equilibrium means your power system, if it is operating here, that is a point, it is your stable equilibrium, means where we are having the steady state operation. If in the after the disturbance here B, if your system is also stable, if you are operating, you are changing slowly from A to B, means you can get another operating state where the system is operating. But if there is a sudden disturbance, your system may come here again, or it may go somewhere else. So we can say here the system is unstable. Here, if it is coming to the another operating equilibrium here, then we can say system is stable. So I'll discuss the region of attraction in the later slides. The voltage instability is defined as it is the absence of voltage stability and the results in the progressive voltage decrease, means voltage your keep on decreasing or increasing, means both are true. Means your voltage is keep on increasing or keep on decreasing, then it is called the voltage instability. Destabilizing controls reaching limits or other control actions, for example load connection, however may be established global stability. The voltage collapse is defined as following voltage instability, a power system undergoes the voltage collapse if the post disturbance equilibrium voltages near loads are below acceptable limits. The voltage collapse in a system may be either total, that is a total blackout, or it may be partial. You can see the various voltage collapse incidences. As you know, it is very difficult when one incidence is taking place, whether it is angle stability case or it is a voltage instability case. But there are some cases it is very clear that looking at the voltage, means normally after getting the disturbance data, we can post-mortem, we can go for the analysis of those data, and then we can identify whether it was the voltage instability or it was your angle stability. So the voltage collapse, which is a phenomena of the voltage instability. So the various incidences occurs, and you can see here the date just we have mentioned here with the location and the time frame this happened. So first that is a reported, although several other, as I said, already there, but here we have listed few here. That is on 30th November 1986, this it happens in the Brazil, southeast of Brazil and the Paraguay, this connection it happens for the 2 seconds. Another here in 85, it was in the South Florida of USA, the time frame was only 4 seconds here. This West Tennessee, here it is for 10 seconds. In 83 it happens in Sweden, it was lasting about 1 minute. Again in 77 there was case in the Jacksonville of Florida, again few minutes, but here you can see in 82 there was several incidents in the Florida state. You can say in 82 after 2 months, again in 1 month here there were 2 cases here, not this is here, means 4 cases were there in 82 itself, and all the phenomena were approximately 1 to 2 minutes. Then another here it was happened in the France, Belgium, again here the France, Tokyo, France and Japan, and again here in the India it happens in 1994, it was the northern grid and it was for a few minutes. And many others in the recent past, the voltage collapse has been seen as a gradual as well as the fast phenomena, hence it requires both static as well as dynamic analysis. Here again some people take the voltage instability as a static case, some people consider as a dynamic, again it depends upon what is your time frame. If it is a time frame is larger, then we can say long term your voltage instability. If it is a time is less, then we can go for the time short term voltage instability case. So the static voltage stability analysis of radial system, here what we do, normally we use the PV curve, which is very popularly used. PV and the QV curves are popularly used to study the static voltage stability of the radial system. Radial system, you know, radial system here, your system which is feeding power here, that is coming from some system, then it is a line and then we have here load. So this is called radial system, means here let us suppose you are having generators, means say a substation which is feeding power over this line, and this is your load which is taking here. So we can draw the PV curve as well as the QV curve for this case, and then we can see at what values and what will be the PV curves and how we can see your system, that means at what loading your system will be unstable. It is related to the maximum loading of the system. As I said, here if you have P here plus JQ, this is a real and reactive loads. If you are keep on increasing these values, keep on increasing, sorry, it's increasing here. So there will be some condition that how much you can load this line. So it is related to the maximum loading of the system. The maximum loading point is also called the nose curve. We will see that. The static voltage stability limit point are the saddle node bifurcation point. Means here you can see, just I will show you, this is your nose point, this is your PV curve, you can say this is a P, this real power you are changing, the voltage of the system is changing. So if you are starting here from there, you can see for any value, just you take for any power factor, let us suppose this is for your unity power factor, this you can see it is following this curve. And this point here for the different power factor it is drawn, here they are the nose point, or it is also called the saddle node bifurcation point. So here the dotted line shows, means your curve which is above this, it is your stable. So these are your stable area up to this nose point. So upper part of this curve till nose point is your stable operating curves. Below this, these are your unstable case. So you can again will see for any particular here power, you will have the two voltages here. For this curve 2, for this curve also we are having 2 voltages, for this curve also we are having 2 voltages, and for this we are having the 2 voltages. So one voltage that is your basically very close to operating voltage, normally it is 1 per unit, and other is very close to 0, or you can say less than 50%. So we are getting the 2 voltage solution of this equation. If we will solve, we will see that. But here this is only your stable points of operation. So here, so that's why this PV curve and QV curve are used for the analyzing the system for your static voltage stability analysis, and the point that is a node point is known as the voltage stability limit point or saddle node bifurcation point. Bifurcation is the point where one part of the system curve, like here if you will see it was like this. So one part here at this point it is stable and other is unstable. So this point is called the bifurcation point, means the bifurcating two curves, one is stable, one is unstable, and they are coming together. So the voltage stability is affected by the various factors. First one is your, as we can see, your load power factor, that is a power factor here, the PF, not load angle. Load type means which type of load we are using, that is it is a thermostatically controlled load which is constant power type, aggravate the situation. Another here is your, that is a generator reaching Q limit, and again Q limit can be hit by the armature and field current limiter reactions, means we are having the different 3 regions as I explained. For PQ, you can say, just in the beginning lectures I discussed about the synchronous generators capability curve, and based on that we saw the field heating limits, your armature heating limits, and another was your end heating limits. So these are the heating limits basically limit your reactive power generation for a given real power output. Another is due to your reverse action of on load type changers, that is OLTC. So they are also affecting your system as well. So the during heavily loaded or stress condition, it becomes difficult to transmit the required reactive power from source to the load. Load here, as I said, this Q once you are increasing, that Q will be met, that we have to supply from here. So again, if it is heavily loaded, it is difficult to provide the reactive power support from here. So this is, you can say, if you are unable to provide that reactive power support, then your system will lead to a voltage instability case. To understand this, we will see one example. So here just I have drawn one here transmission line. We have ignored its resistance. However, you can take the resistance and then you can write the voltage equation, means you can write the power equation, current equation, and then finally you can calculate this voltage of this bus V for a given P and Q. If you are ignoring the losses of the line, means that R is neglected, just we have only taken this reactance, that is Jx, and this is a radial line because it is only one load here, it is feeding, there is no other interconnections, and this is your, you can say, infinite bus, or just you are feeding from here large power system. So the power which is flowing in this one is from source to again the load. If your P and Q are changed, your the power here will be drawn, will be changed. So what we can write, this power which will be flowing here, taking this as a reference, because here I have written the voltage magnitude V angle 0, this is your E angle delta. So the delta is more, so power will be flowing from the higher delta to lower delta. And as usual we can write here the power flow in this one is EV, that's voltage magnitude here as well as here multiplication divided by x of this line, sin delta, and delta is angle difference between these two buses, that is a delta. And similarly here this reactive power we can write here, that will be the reactive power will be flowing is a negative because here it is coming to this node. So this is your V upon x, here V minus E cos delta. From here again, if you want to avoid this reactive power, how much it is injecting to system, then here it is E cos delta minus V that will be appearing, and then E minus will be inside, so there will be no problem. If we can eliminate the delta, because delta we don't know and it is very difficult to measure also, although it can be measured, but it is very difficult. So we can eliminate from here delta. Simply what we can do here, we can write the sin delta. Sin delta will be nothing but your P upon EV, and here it is your x. Similarly here we can write your cos delta. From here we can write this value, we can subtract finally. So I can write this will be going this side, so it is your Q plus here V square upon x, we are adding this value V square upon x that side, and then this will be okay, so it will be adding, and then upon here it is your E V upon x. So what is happening here, you can see, if you are just simplifying cos here, if you are squaring and adding, we will get a equation, means what will happen here, xp over EV here is square plus here your x VE Q plus V upon x square here, and again for whole square, that is your unity. As you know, sin square delta plus your cos square delta will be unity. Now you can see here, if you are eliminating this V term here again is square, we will get the order here V square is there. So square of that, it is a, it will giving the equation of, we can write the voltage, that is your terminal voltage here, and we will get the order of 4 here we are getting equation. So it means we are getting fourth order of equation, means it will have the 4 roots. However, only the 2 roots are feasible, other roots will be having the negative, so we cannot take that, and that will be imaginary. So always we know the voltage will be the positive real value. So we can again, ignoring the other 2, we can get the 2 roots here V1 and V2, that will be again we can write in this way. Means writing this equation, we can get the V square in that term, and then we can take under root here, you can say here under root we have written. So you can see we are getting the voltages in terms of P and Q, maintaining this voltage is constant, because we are assuming this generator is maintaining the voltage, the system where it is feeding is a constant. So fixing this value, x is fixed, we can, if we are changing P, we can get the V relation, and then we can go, we can have the PV curve. Similarly, if changing Q, keeping P constant here, and the V if you are getting, then it is your QV curve, and then we can get. So for given P, means fixing Q, a value of P, 2 voltage solution exists, one higher than other, means one will be higher because here plus minus, one is adding, another is subtracting. So if P is increased, the higher solution value decrease and the lower one increases, means the lower one, which is the lower voltage, it will be keep on increasing, however other will be decreasing, means it is going to coincide somewhere. For higher value of Q or poor power factor, both P critical and the V critical reduces, and you can see this curve here very well. So what is happening, you can see the one voltage here for this is a increasing lower one, and other one is decreasing, and it is like this. Again with the changing the power factor, means the reactive power support at that bus you are changing, you can see this value is keep on changing. So this is your effect of load on the power factor. We can say if it is a normal unity power factor, this is your lagging. If you are leading the power factor, you can again have the more loading. So at this point you cannot load, suppose your power factor is unity power factor, not UPF, you cannot load more than this. So in this case, to load this you have to go for some leading power factor, or you can use some reactive power compensator for that. You can use some reactive power capacitor, etc. Then you can go up to here point and keep on you can increasing. So this is means you have to have the better power factor to avoid the instability. So we can directly see it is directly related with the reactive power. So the voltage instability is the case which is directly related to the stability of the system.